Arthur McDonald, Professor Emeritus of Subatomic Physics and Particle Physics at Queen's University and Nobel Laureate, is the next recipient of the 2018 Distinguished Alumni Award. To describe his illustrious career in nuclear physics, Dr. McDonald invokes the subtitle of his mentor, Willie Fowler's 1983 Nobel lecture, Ad Astra per aspera et per ludum, which Dr. Fowler translated as, to the stars through hard work and fun. This is a spirit that I've always respected for research, work, education, and collegiality. Dr. McDonald earned a bachelor's and master's degree in physics from Dalhousie University in Nova Scotia, where he was born. He completed a PhD in physics at Caltech in 1969, moving back to Canada for a postdoctoral, then permanent position at the Atomic Energy of Canada Chalk River Nuclear Laboratories, with an emphasis on experiments that demonstrated parity violations. Dr. McDonald subsequently joined the faculty at Princeton University, where he collaborated to develop polarized targets that enabled a variety of nuclear and particle physics measurements and eventually medical imaging. In 1984, he became involved in the development of the Sudbury Neutrino Observatory, the SNO collaboration, an ambitious and challenging effort to build a heavy water Cherenkov detector designed to identify neutrinos produced by fusion reactions in the sun. The goal was to understand the cause of the large discrepancy between the modeled versus the measured number of neutrinos traveling from the sun to the Earth. Over the next decade, Dr. McDonald became director of the SNO Institute and a US spokesperson for the project, while the group acquired more partners and designed the detector. In 1988, he took a sabbatical at Queen's University to help develop SNO's final design and funding proposal, and accepted a faculty position at the university the following year. Construction of the SNO laboratory began in 1990 in a nickel mine near Sudbury, Ontario, 2,000 feet underground to shield it from cosmic rays. The detector is a 12-meter diameter acrylic vessel filled with 1,000 tons of ultra-pure heavy water, encapsulated by a giant geodesic sphere containing almost 10,000 sensors that detect the tiny flashes of light emitted as neutrinos are stopped or scattered in the heavy water. The experiment resolved the solar neutrino problem by providing direct evidence that neutrinos oscillate, switching from one type of neutrino to another along their path from sun to Earth, and thereby must have mass. Dr. McDonald received the 2015 Nobel Prize in Physics jointly with Takaaki Kajita for this insight into the fundamental constituents of matter, as well as the 2015 Breakthrough Prize in Fundamental Physics, which he shared with the entire SNO collaboration. Art.
I feel very honored and very humbled by this award from this wonderful institution. I've been reminiscing since I arrived yesterday about the many things I learned here at Caltech, and one of them is that at this time of year I'm extremely allergic to olive tree pollen. So I'm hopeful that you'll bear with me through this if I sneeze a couple of times. So I grew up in a small city in Nova Scotia on the far eastern coast of Canada, and I developed a strong interest in physics in my education at Dalhousie University. When I came to Caltech in 1965, it was like another world in which the latest subjects in physics ran past your door every day. And yet the professors and others with whom I worked treated me in such a considerate and human way and taught me that the pursuit of science is fun. I had a great supervisor for my thesis, a Canadian named Charlie Barnes, in the Kellogg Radiation Laboratory, headed by the legendary Willie Fowler. Willie received the Nobel Prize in Physics in 1983 for developing an understanding of how the chain of nuclear reactions in the sun and other stars generate elements from which our universe is composed, and also in the process generate enormous numbers of neutrinos. Kellogg was indeed a fun place to work in the late 1960s with a great sense of camaraderie as well as a sincere respect for research quality. The seminars were at 7:30 on a Friday night, usually followed by a party at one of the professors' houses with the Kellogg band providing musical background, and Charlie was a pianist, and so it was often at his house. The discussions in Kellogg and at the parties ranged from the fundamental laws of physics to how the universe as a whole was composed. Now, the nuclear reactions related to nucleosynthesis in stars and fundamental symmetries in nuclei were being measured in very painstaking experiments in 3 different accelerators within the Kellogg Radiation Building. In the summers, Ray Davis from the Brookhaven National Laboratory visited, and he was following an idea that one could observe neutrinos from the sun with a large tank of cleaning fluid in an underground laboratory. John Bacall was a junior faculty member at Caltech, and he'd been developing a combination of nuclear physics and models of the sun that led to the prediction for how many neutrinos you might detect. At the same time, Richard Feynman, who taught my quantum mechanics course, actually, a wonderful experience, and Murray Gell-Mann were working on topics that formed the basis for the standard model of elementary particles. This was amazing stuff for a wide-eyed 22-year-old from Nova Scotia. Charlie Barnes and others inspired me to always seek answers to questions that would be important for our understanding of the laws of physics. And so for my thesis, I studied symmetries induced by the electromagnetic force in nuclei, and I went on to study effects of the standard model in nuclei, in some cases effects as small as a few parts in a million. In 1984, when our team started developing the Sudbury Neutrino Observatory project, many of the contacts I'd made when I was at Caltech in what turned out to be an 18-year scientific quest had Caltech connections. 4 of Charlie Barnes' students actually were collaboration members out of about 70 faculty members overall. Because Ray Davis's experiment, as has been said, had shown too few neutrinos from the sun compared to John Bacall's calculations. And this came to be known as the solar neutrino problem. It had great potential for new science. The thought was that either the calculations that matched all other properties of the sun had to be modified, or else the electron-type neutrinos produced in the sun were changing to the other 2 types and escaping detection in Davis's experiment. And this oscillation process would require changes to the standard model of elementary particles at a very basic level and certainly was not expected. However, that process, in fact, was exactly what we observed, and it required extensions to the standard model that involved finite mass for neutrinos. We had built an ultra-clean neutrino detector the size of a 10-story building, 2 kilometers underground to remove the cosmic radiation, and filled it with $300 million worth of heavy water that we had on loan for $1, which is pretty good leverage in any market. The heavy water enabled us to observe the other types of neutrinos that were escaping Davis's measurement, and that's how we were able to make our discoveries. We also validated, very accurately actually, John Bacall's calculations for the sun that had been questioned for over 30 years, and it led him to comment that he felt like he had been absolved from a heinous crime by new DNA evidence. In retrospect, there were many Nobel Prizes associated with the science to which I was exposed at Caltech. Willie Fowler, Ray Davis, and myself for the physics of the sun and solar neutrinos. Richard Feynman and Murray Gell-Mann for the basis of the standard model. And in fact, Murray Gell-Mann is a co-author on what is now one of the most accepted theories for finite mass for neutrinos. Kip Thorne and Barry Barish were young junior professors at the time when I was here, but Barry was later the chairman of our advisory board for the Sudbury Neutrino Observatory during the 90s. So it's a great pleasure for me to be here at Caltech 50 years later for this wonderful award and to pay tribute to the nature of Caltech itself and to its influence on me. This truly is a wonderful institution. Thank you very much.